Hello, I'm Dan Esposito, and I'm the PI of the Solar Fuels Engineering Lab in the Chemical Engineering Department at Columbia University. My lab's research is motivated by the need to develop sustainable energy technologies that can eliminate society's reliance on fossil fuels. Towards this end, our research focuses on low-temperature electrochemical and photoelectrochemical technologies that use sunlight or solar-derived electricity to convert low-energy molecules like water and carbon dioxide into storable chemicals and fuels. Besides serving as an energy storage media, these so-called solar fuels are expected to be very important for a sustainable energy future because they can be used to reduce the carbon footprint of a wide variety of end-use sectors. Ultimately, the primary mission of my lab is to teach aspiring chemical engineers the fundamentals that underlie solar fuels technologies so that they are well equipped to pursue a career in research and/or work in industries where they can put those skills to use in the real world. Research activities in my lab are organized into three complementary areas. First, we develop photo and electrocatalytic materials that are critical to enabling electrochemical conversion processes that are efficient, selective, and robust. Second, we investigate new reactor concepts that offer inherent advantages compared to conventional electrochemical devices. Third, we use and develop analytical tools that allow us to characterize the properties and performance of these materials and devices with high spatial and/or temporal resolution while they are operating in the electrochemical environment. The knowledge gained from these tools, combined with modeling work carried out in our lab or by our collaborators, allows us to develop quantitative design rules that relate key performance metrics of solar fuel systems to the chemical and structural properties of system components. Because our work involves both devices and materials, we think about design problems that span a wide range of length scales. Our research on catalytic materials often leads us to ask questions that relate to their nano or atomic scale characteristics. For example, we are actively investigating electro and photocatalytic materials where the catalytic active sites are encapsulated by nanoscale overlayers such that the reactions of interest occur at buried interfaces, such as those shown here. In these materials, we want to understand how variations in the nanostructure and composition of these ultra-thin overlayers combined with the chosen operating conditions affect the activity, selectivity, and durability of catalytically active buried interfaces. We also think a lot about problems characterized by larger length scales. For example, the performance of devices we develop in our lab is often highly dependent on processes and components that are characterized with macroscopic length scales. Here, you can see an in-situ high-speed video of a membrane-free electrolyzer where we are interested in transport phenomena occurring over length scales measured by millimeters and centimeters. Regardless of the relevant length scale, it is our objective to develop the design rules that govern the performance of these emerging solar fuels technologies and to use those rules to better understand the trade-offs between efficiency, cost, and durability while creating a framework for optimizing their performance for real-world applications. Overall, many challenges remain in the field of solar fuels, and I believe that chemical engineers are uniquely positioned to address many of them. Our group is always looking for motivated and talented students to join the group, and I hope you will take the time to further explore our website, as well as those of our collaborators in the Columbia Electrochemical Energy Center and the Lenfest Center for Sustainable Energy.